Okay, so good morning, everyone, to this morning session. So the first speaker is Sylvie Corteel, and she will tell us about the partitions, vertex models, and tilings. Thank you.
So thank you for the invitation. Thank you to Filippo to be the best organizer ever. And actually, this talk is the introduction to the talk of David on Monday. But I know that a lot of you are leaving this weekend, so I hope that you will be motivated to watch it on Zoom on Monday morning. Okay, and I'm gonna give like kind of an introduction with not too much details or not much technical details. Okay. So my favorite object in this talk, or maybe most of the time, are integer partitions. So I call a partition lambda to be a sequence from lambda 1 up to lambda k. They're going to be non-negative integers, and they are put in non-increasing order. Okay. So most of the time I care if it's a partition of a given integers, but I won't tell too much details about that. But let me start with an example. Okay, so if I take lambda to be 4, 3, 1, most of the time I like to draw it. Okay, I'm going to make a lot of drawings in this talk. And so one way to draw partitions is called a Ferrar's diagram. So I take the first part of my partition, which is 4 here. I draw 4 cells, and then I go to the next row. I'm going to draw 3 cells and 1 cell. And here I left justify my cells. Okay. So that's very useful for many reasons. And one of them also is because after we want to fill these cells with some numbers. Okay, but also in this talk, I'm going to change writing those partitions are sequences of integers to writing those partitions are an infinite word. Okay, with 2 types of letters or things that will be particles and wholes. Okay, so I take my partition 4, 3, 1 here, 4, or maybe it's not 4, 3, 1 here anymore. 4, 2, 1. Okay. So there's going to be a lot of mistakes in my talks. So bear with me. Okay. And then I rotate the diagram. And now I'm going to read the border of the diagram. Oops. Okay. Starting here. So I'm going to go infinitely down. And then at some point, I'm going to go up, down, up, down, up, up, down, and then infinitely up. Okay. And I change this reading word of my partition by a sequence, okay, of black and white, where you saw already what I'm doing. When I go down, I put a black. And when I go up, I put a white. Okay, so this word is doubly infinite. Okay, it starts with an infinite number of black. It ends with an infinite number of white. But as you can see in the partition here, there's a unique center. And it's easy to find this center. It's the position where the number of black to the right is equal to the number of white to the left. Okay, so even though I have a doubly infinite word, I have a unique way to center this word. But now I don't want to look only at one partition, but I'm going to look at sequences of partitions. Okay, so let's start with a pair of partitions. I'm going to say that lambda interlaces with mu. Okay, if when I looked at the parts, lambda 1, lambda 2, mu 1, mu 2, I can just take the parts of lambda and mu and interlace them. Okay, so that's what I mean here. I want that lambda 1 is greater or equal to mu 1, greater or equal to lambda 2, greater or equal to mu 2. Okay, and as I draw right under that, if I looked at my 2 Maya diagrams of my partition, they're going to interlace if and only if I start at the rightmost black of lambda and then join the rightmost black of mu and continue like that. Okay, I'm going to do this nice zigzag. Okay, that shows really the relation between interlacing and having these Maya diagrams kind of interlacing themselves. Okay. Because the parts of my partition lambda corresponds to the black particles. Parts of my partition mu corresponds to also the black particles. And they interlace if and only if I can zigzag like that using those beams. Another way to see that, okay, in combinatorics, we say that lambda and mu interlace if and only if I draw the Ferraz diagram of lambda and I draw the Ferraz diagram of mu. So here I took an example, hopefully with no mistake. So 7, 4, 1, that's my lambda, and mu is 5, 1, 1. Okay, and if I take the difference between those two diagrams, so first of all, the diagram of mu is included in the diagram of lambda. And then if I look at the cells here, in each column, I have at most one cell. Okay, so this column has 0 cell, this one has, these 3 columns have 3 cells, like that. Okay, so that's what we called usually a horizontal strip. Okay, so it's a skew diagram that has at most 1 cell in each row. So why do we care about interlacing partition? For many, many reasons, okay, but one of them is that there's a bijection between semi-standard Young tableau of shape lambda that I'm going to define, such that the entries are less or equal to n, and then a sequence of interlacing partition, lambda 0, lambda 1 up to lambda n, with the condition that whenever I go from lambda I to lambda I plus 1, I interlace. Okay, and then also the first and last partition are fixed. Namely, the first partition is empty, and the last one is the shape of my tableau lambda here. Okay. So let me give you an example. Okay, so lambda is again, we're back with 4, 3, 1. I fix n to be equal to 4. Okay, and what's a semi-standard Young tableau is a filling of the cells of my partitions with integers less or equal to n. These integers are positive. And I want this filling to be weakly increasing in row and strictly increasing in columns. Okay. So how do I go from my semi-standard Young tableau to a sequence of interlacing partition? So I said my first one is fixed to be the empty partition. And then how do I get lambda I? That's the shape of the entries less or equal to I in my partition. Okay, so I look at the entries that are equal to 1. That gives me the partition 2. The entries that are equal to 1 or 2. Okay, that gives me the partition 3, 2. The entries that are less or equal to 3, that gives me a partition 3 to 1. And the entries that are less or equal to 4, that gives me the full shape of the partition. Okay, and because of these conditions, weakly increasing in row, strictly increasing in column, okay, it's easy to see that it's the same of being a semi-standard Young tableau and be a sequence of interlacing partition. And these objects in combinatorics, they're very important because they have the combinatorial model for sure polynomials that have lots of links and that are nice symmetric polynomials. Okay, so I could give a whole talk on that, but I'm not going to talk about them today. Okay, in the same way, maybe that's another way that you know how to look at these sequences of interlacing partition. Okay, you can see them as Gelfand settling pattern. So what's a Gelfand settling pattern? I put my partition lambda on the top, okay, and I'm going to fill the whole triangle such that the rows are going to be weakly decreasing, and the diagonals this way are weakly decreasing, and the diagonals this way are weakly decreasing. Okay, and you can see easily, okay, I wrote my sequences of interlacing partition, and they just correspond to exactly the rows of my Gelfand settling pattern. Okay, so I'm talking again about the same objects over and over, but we're going to see that it's not the only one. Okay, So sequences of interlacing partitions are the same as semi-standard Gantt tableau or these get-found settling patterns. But let's go back to when we look at a Maya diagram, okay? And I'd like to see my sequences of interlacing partition as a sequence of Maya diagram. So you have to believe, okay, I wrote the Maya diagram corresponding to the empty partition, the partition 2, 3, 2, etc. You can see that indeed, what I see on the Gelfand settling pattern, you can see it also on the Maya diagram, these interlacing conditions, okay? And so I can see a bijection between these and these sequences of interlacing Maya diagrams that are gonna have some special conditions. So how do I go from a sequence of interlacing Maya diagrams to what we really like in combinatorics, non-intersecting lattice paths? Okay, so I draw here my 5 Maya diagrams, the empty 2, 3, 2, 3, 2, 1, 4, 3, 1. And then I'm gonna draw a path going north and east that are gonna link my particles, okay? So I start here with the rightmost particle. I'm gonna go up and to the right until I hit the next particle, the rightmost here, and I'm gonna continue, go up, go to the right, and I do that for all my particles of my Maya diagrams. Okay, so I claim again that this is a bijective process, and it's very easy to go back to my semi-standard Young tableau. I'm just gonna look at the horizontal step here in my non-intersecting path, and I'm gonna look at which height they appear. Okay, so here for the rightmost path, I have 2 steps at height 1, 1 step at height 2, and 1 at height 4. And so that's how I fill the first row of my diagram. 1, 1, 2, 4. Okay, same for the next one. Okay, I have 2, 2, 4, and 3 here. Okay, and again, it's not too hard to see that being a sequence of interlacing partition is going to give you the fact that the paths are non-intersecting and that the tableaus are weakly increasing in row and strictly increasing in columns. So now I went from my tableau to my sequence of interlacing partition. Now I want to make a bijection, okay, with tilings. So what I'm going to do is I'm going to have a very simple rule. Whenever I have 2 particles linked by a vertical edge, I'm going to put a square. Okay, when I'm going to have 2 particles where here I have an east step, I'm going to put this type of lozenge. And then when I'm going to have no particle, I'm going to put this third type of things. Okay, and I didn't do the whole drawing, but you can see that if I continue with these rules, okay, I'm going to fill completely my sequences of Maya diagrams. So what do I get? Okay, now I have a sequence, a bijection between my sequences of Maya diagrams and some lozenge tilings of a given shape. Okay, so what do I mean by lozenge tilings? I mean, I use 3 kinds of lozenges that I have here: yellow, pink, and blue. Okay, and these will always have some kind of trapezoidal shape because they are fixed here, the bottom to be the empty partition. So here the bottom is here and the top is here, the way I drew them. Okay, and the top is given by the Maya diagram of the partition lambda. Okay, so that's the case where lambda is a rectangle, and here where lambda is a more tangent. And again, you see easily that if I give you the non-intersecting path, you can build those lozenge tilings. Or if I give you the lozenge tilings, it's very easy to get back the non-intersecting path because the bijection is written here. Okay, so I didn't use the same bijection on the 2 pictures. But on the top one, okay, I put a path going through the blue tiles, a path going through the yellow tiles, and no path going through the purple tiles. Okay. And the bottom, I made another choice. Okay, I chose purple and blue, but not yellow. But as you can see, you can change the three types of lozenges as long as you put a path on two kinds of lozenges. You're going to get back your non-intersecting paths or your sequence of interlacing partitions. Okay. So now I want to move from these ideas and now use what I'm gonna draw in a weird way, but what are vertex models. Okay, so I take my same picture I had before. Okay, so I have my sequences of interlacing partitions. I draw my non-intersecting path, but now on each cell I add a little square. Okay, and as you can see, now I have a kind of puzzle that use 5 different pieces, and that's the 5 different pieces that you can see. Okay, I can have a white cell. Okay, I can have a cell that has a path that goes up. I can have a cell that has a path that arrives from the left and go to the top. So here. Okay, I can have a path that goes straight, this one, and a path that enters in the bottom and goes to the right. So I changed my idea of looking at sequences of interlacing partitions to a way of building this kind of puzzles. So what do I mean by that? I mean that I take a sequence of infinite cells, square cells like that. Okay, I fixed the left-hand side to be empty, the right-hand side to be empty. I fixed the bottom to be the Maya diagram of the empty partition. I fixed the top to be the Maya diagram of a given partition lambda. And now I'm going to look at all the ways, okay, to put my 5 little pieces of puzzles so that, of course, the pieces match, okay? So if I have a cell like that on the right, I cannot put a cell like that, okay, because the path must continue in my model. Okay. So now I want to see my sequences of interlacing partition, okay, as this kind of vertex models, where I fix the bottom, I fix the top, the left and the right, and then I sum on all the different configurations I can do. So if I do that, okay, can I look at other combinatorial objects? So I'm going to try to explain to you, yes, okay, that helps to count some other objects. And let me give you an example, okay? So we're going to be a bit in the same word as before. So I fix a shape, lambda, 431, okay? And now I fill it with non-negative integers. No, I can have 0 or positive integers. And now I relax what I had on the semi-standard Young tableau. Okay, I weakly increase in row and weakly increase in columns. Okay, usually that's what we call reverse plane partitions. And my goal is to count. I have an infinite number of objects. Okay, I want to count those objects when lambda is fixed. And then I count them according to the sum of the entries in my reverse plane partition, which is the weight of the reverse plane partition. And how can I do that using vertex model? So I'm going to do again some kind of rotation of my Ferrar's diagram. Okay, the same as before, except now I have 431 again. Okay, I'm taking my reverse plane partition. I'm writing it this way. And now I'm going to see it as a sequence of interlacing partitions. Okay, so what do I mean by that? I'm going to read now that I make this rotation, the columns of my reverse plane partitions. And my claim is that when I read the border of lambda, that tells me exactly how the partitions interlace. Okay, so I claim that if I looked at the reverse plane partitions of this shape, they're going to correspond to this sequence of partitions. Okay, and you see that sometimes we have less or equal, and sometimes we have greater or equal. So I claim that we are going to have a less or equal whenever we go up. Okay, so I start and end with the empty partition. And whenever I go up, I claim that my partitions are going to interlace towards something bigger. And when I go down, they interlace towards something smaller. Okay, so here you can see that 3 is greater or equal to 1, which is less or equal to 1, 0, which is less or equal to 4, 1, greater or equal to 3, and less or equal to 4, and greater or equal to 0. Okay, so I change my enumeration problem of counting these reverse plane partitions to counting some sequences of interlacing partitions that sometimes increase and sometimes decrease. Okay. So why is that interesting to do that? And why can it be helpful to count these combinatorial objects? Okay, so this is helpful because we're going to see in a minute. Because if I want to compute this generating function, so I sum on all the reverse plane partitions of shape lambda, Q to the sum of all the entries in the reverse plane partition. The result, that's very classical, is that it has a very nice product formula for any lambda. So I take the product on all the cells of the lambda, and it gives you 1 over 1 minus Q to the hook of the cell. Okay, and so maybe a lot of you know what a hook of a cell in a diagram is, but let me remind you. So the hook of a cell, for example, this one, is the number of cells to the right plus the number of cells under plus the cell itself. Okay, so this cell has hook 4, but this cell here has hook 6. And so the claim is that this generating function, okay, the generating function of this object is exactly this nice product here. So how do I do that? Okay, so how can I prove such a formula using vertex models? So I just introduced you a vertex model that tells me that I'm going to have a configuration between mu and lambda if and only if they interlace, and lambda is greater or equal to mu. And you can also, in the same way, write another 5 vertex model. Okay, basically it's the same one, except now the border condition on the right is different. Okay, now I'm going to have a particle exiting on the right. Okay, and so I can build the same vertex model, and I'm going to have a configuration between lambda and mu if and only if mu is less or equal to lambda. So just stop me if things are not clear. I might be the only combinatorialist here. So, okay. So what I just did is I changed my problem of enumerating this kind of reverse plane partition to a vertex model. Okay, I claim I have a bijection between the reverse plane partition of this shape and the vertex model with these conditions. Okay, so here I have again the empty partition, the Maya diagram. On top, I also have the empty partition. The shape lambda tells me how I put white and gray rows. Okay, because when I go up, I put a white row, and when I go down, I put a gray row. Okay, so that's why I have white, gray, white, white, gray, white, gray. Okay, and the border on the left is always empty. And on the right, I have a particle for a gray row and no particle for a white row. Okay. So this, I just did something just bijective. Okay, I transform my problem of enumerating reverse plane partition to a problem of looking at vertex models. Okay, and you have to believe me that this reverse plane partition, okay, is going to transform to this configuration on the right. Okay, because for example, the partition here 3 will have exactly the Maya diagram here 3. Okay, so you can see 3, 1, and then 1, 0, 4, 1, etc. Like at each stage, you can see the partition. Now, what do I do when I did that? How can this be helpful? Okay, so you might be able to guess. Okay, what I'm going to do is I'm going to use the Young-Baxter equation. Okay, on the left, I'm going to put another vertex, and I'm going to find some equations on this vertex on the left to be able to push it to the right. Okay, and when I push it to the right, and I have a white row at the bottom and a gray row on top, that's just going to switch me the 2 rows. Okay, and using this Young-Baxter equation, you have to believe me that I can transform the partition function on the left here, where I had a mix of white and gray rows, to the partition function on the right, where all the gray rows now are at the bottom. Okay, and this, the weight of the cross here is going to give me exactly the product of the hooks that I was looking for. Okay, so magically, just using the Young-Baxter equation, the hooks pop up naturally. Okay, and then I get the partition function on the right. And so why am I happy to have gotten that? Okay, why now it's become an easy problem is that you can see that on the right, you don't have many choices. Okay, indeed, you have one unique configuration that can be drawn. And then, even though I didn't define you the weights of the vertices, it's working perfectly that this will have weight 1. And so that you can get exactly that the generating function on the left is exactly this product of hooks. Okay, so I hope I convinced you by using this vertex model that you can transform a hard enumeration problem into something easy just by using the Young-Baxter equation. Okay, so now I want to look at another things on partition, which is called the conjugate partition. Okay. So when I defined my partitions, so my favorite example 4, 3, 1 here, okay, I said that I would put 4 cells in the first row, 3 cells in the second row, and 1 cell in the third row. But as you can see, if I read now my Ferrar's diagram, not going through rows, but going through columns, I get another partition, namely here, 3, 2, 2, and 1. Okay? And so that's what's called the conjugate partition. Okay? So whenever I have a partition, I can switch rows and columns and get another partition. Okay, so what do I mean when I do this operation? What kind of operation does it give me on the Maya diagram of the partition? Okay, so you have to believe me, this is the Maya diagram of 4, 3, 1. Okay, and I claim that to get the Maya diagram of the conjugate, you do 2 very simple things. Okay, first you complement. So any black becomes a white, because you can see here, you're going to switch the horizontal step to vertical steps whenever you go to conjugate. But you also have, after, to take the mirror, okay, because this is not a proper Maya diagram. I told you that they have an infinite number of blacks on the left and an infinite number of white on the right. Okay, so after you complement, you must also mirror, and then you're going to get the Maya diagram of the conjugate. Okay, so on the Maya diagram, it's a pretty simple operation. So why do I care about that? Is that you also have this condition now of co-interlacing. So I'm going to say that lambda co-interlaces with mu if and only if I take the conjugate of lambda and mu and they interlace. Okay, so if you think about the condition I gave you before, that lambda and mu were interlacing if and only if there's Q diagram at most one cell in each row. When you conjugate, you get the same thing, except that two partitions co-interlace, if and only if I'm going to have at most one cell in each column. No, before columns, now a row, okay? So now we have a vertical strip, a Q diagram that has at most one cell in each row. Okay, and so let's do the same games that we've done before. Okay, I take two partitions, their Maya diagram co-interlace, and now I'm going to do the same game as before. I'm going to draw some path between the particles of the two Maya diagrams. Okay, so here is what happens, is that finally the paths can go up or at most one step to the right. Okay, it's not very hard to see. Okay, but now the path, okay, they can touch each other. So I don't have any more non-intersecting paths when I draw them this way, but the path cannot go two steps to the right. Okay, and so now if I looked at sequences of co-interlacing partition, that's going to give me the conjugate of semi-standard Young tableau. Okay, and the vertex model I get is again a 5 vertex model, just as before, except now the puzzle pieces are a bit different. Okay, namely that we have these 4 pieces that were like before, but now I cannot have the path that just go horizontally, but I can have this last piece. Okay, so I change my problem. I have another vertex model that has 5 different types of vertices. Okay, I fix the same game as what I've done before. The bottom is the empty partition. The top is the shape lambda I want to fill. And I fill my vertices with these 5 different types of vertices. Okay. And so the question you can ask is, what do we get now if I mix these interlacing and co-interlacing things? And so that's what, I don't know if it's me, Jeremy, or Guillaume. One of us gave this talk here 7 years ago, so you all remember. Okay, and what you get are domino tilings. Okay, so you'll get some tilings on an infinite strip with some border conditions that are in bijection with this kind of interlacing, co-interlacing family. So let me give you an example, okay, which is one that you probably all know very well, how to see domino tilings of the Aztec diamond as a sequence of interlacing and co-interlacing partitions. So the Aztec diamond is a diamond shape with a fixed number of corners. Here, m is equal to 3. And you want to fill this shape, okay, with dominoes. So you've seen maybe several talks about the Aztec diamond, including the one of Philippe Ruel during this program. Okay, so I have vertical dominoes and horizontal dominoes. So it's very well known that it has a beautiful enumeration formula. If you fix m to be the number of corners, then the number of domino tilings of the Aztec diamond is 2 to the m plus 1 choose 2. And so here for m equals 2, this is going to give you 8, and I listed you the 8 domino tilings of the Aztec diamond. So now, how do I go from a domino tiling to a sequence of interlacing partition? Okay, so you have to remember, when I draw you the Aztec diamond, I draw it with gray and white cells. Okay, I did a checkerboard of the plane. And you can see now that we are going to have some vertical dominoes that have a gray cells on top, and some vertical dominoes that are going to have a white cell on top. Okay, so I'm going to do this very easy bijection from my tiling to sequences of holes and particles. So whenever I have a vertical domino with a gray cell on top, I fill it with 2 holes. A white cell on top, I fill it with 2 particles. Okay, when I have a horizontal domino, I have also the same things. If I have a white cell to the left, I put 2 particles in it. And if I have a gray cell to the left, I put 2 holes. Okay, so, and now you could forget the dominoes. You can easily go back from these sequences of particles to the domino tiling. Okay, now I'm going to do a bit the same game as before. Okay, except I'm going to read now the tiling diagonal by diagonal, like that, from the southeast to the northwest. Okay, and my claim is that if I read here the Maya diagrams of these partitions, it's going to give me exactly this type of sequence. Okay, I'm going to start with an empty partition and with an empty partition, and then I'm going to go co-interlace going up, followed by an interlacing going down, co-interlace going up, interlacing going down. Okay, so I have a bijection between the domino tilings of the Aztec diamond and these sequences of interlacing, co-interlacing. So when I go up, I co-interlace, and when I go down, I interlace, and I go up, down, up, down, up, down. Okay. And so if you want to compute after the generating polynomial, so M is fixed, and X and Y's are going to follow the weights of each partition on each diagonal. Okay, and then you can easily see, and I'm going to give you a one-line explanation after, that this generating polynomial is going to give you this nice product formula. Okay, the product from 1 less or equal to I less or equal to j less or equal to m of 1 plus xi yj. Okay, and of course, if I put x and y to be 1, I get back my 2 to the m plus 1 plus 2. And again, why you get this nice product formula is that I transform my problem of domino tilings into a problem of partitions that are interlacing. So I change my problem of domino tilings to a problem of vertex model, where here I have the empty partition, on top the empty partition, and then I have these types of vertices, okay, gray, purple, gray, purple, gray, purple, gray. And I use the Young-Baxter equations to put all my gray on the bottom, all my purple on the top. And I do exactly what I've done before with the reverse plane partition. And now the factor I get is exactly this one. Okay, so I hope I convinced you that whenever you want to count something, whether it's hexagonal tilings or domino tilings, going through vertex model is the easy way to go. And what you only need is have a Young-Baxter equation. Okay, so then you can do lots of asymptotics, but that's not the goal of today. Maybe you heard that from the talk of Vadim, and for many, many things, there's a whole field now that says those things. But I just want to mention a recent paper of Zhang-Yang Li that gives a kind of general setting, okay, to compute the Arctic curve of all these models. So when we mix this idea of co-interlacing and interlacing, we wrote a paper that was called Rare Liard graphs, okay, with Cédric Boutillier, Jérémy Boutier, Guillaume Chapuis, and Sanjay Ramassani. And recently, there's a paper of Zhang-Yang Li that explained you how to do asymptotics for all these families in kind of an automatic way. Okay. So that's basically what I wanted to say, but I'm going to just give you a few hints of why this is cool and why, when you generalize this idea, you can get some very nice results. Okay, so the first thing that's been really active recently is to look at this vertex model, not just as a rectangle, but to put them on the cylinder. Okay, so that's what we call cylindric partitions. Okay, I have my border as before. I'm going to fill it with integers with the same conditions as before, but now I have my sequence of interlacing partition, but I don't force the first and last one to be the empty partition. I force them to be the same partition. Okay, so that's what I draw here. The 4, 3 here and the 4, 3 are the same thing. You can see now my reverse plane partition as an object on the cylinder. Okay. So when you look at the vertex model, okay, Now it's a bit different. I still draw it because I can't do a cylinder. I still draw it as a rectangle, but what I do now is I want the bottom and the top to be the same thing, and then I summon all the partitions. So equivalently, I just see it as a model on the cylinder. Okay. So there's lots of nice results about that. So that was an idea introduced in the 90s by Gesell and Krattenthaler. But recently, there were a lot of asymptotic results on these cylindric models. And maybe you heard some talks about that too. But me, I'm interested in those models in a very different perspective, which is I guess my main hobby is to prove some like identities of hypergeometric series, like Rogers-Ramanujan identities using these objects. Okay, so I won't give you any details because that's not the subject of this workshop. Okay, so one generalization that you can think about is now not look at that on the plane, but put this vertex model on the cylinder. So another thing you can do is you want this to not be anymore just looking at rectangles, but looking at vertex model of other shape. Okay, and this is what my student in Berkeley is doing, Freddy, is to look at this vertex model on this kind of staircase shape. Okay, so I do the same as before, except my bottom partition now is on a staircase, and my top partition is a partition lambda. And you can see again these objects as certain domino tilings. And one special case about that is something that Philippe Di Francesco talked about, is you can make a bijection between this vertex model on staircase shape and certain domino tilings of this shape, where the lambda here correspond to the southeast part. Okay, and there's a very beautiful conjecture of Di Francesco that these domino tilings have a nice product formula. And I think that nobody knows how to prove this, and seeing this as a vertex model for now hasn't been helpful to give a proof either. But there are some very cool combinatories coming from looking at this vertex model, not anymore on a rectangle, but on different shapes. Okay, and the last thing I want to advertise is something that David is going to talk about, is now you don't only look at one vertex model, but you look at colored vertex model. Okay, so there's many papers about that right now. So what you do is you're going to take your 5 vertex model, but you're going to superimpose them. So what do I mean by that? So that was my white vertices, my 5 vertex model that I colored blue. But now I'm looking at pairs of 5 vertices, now with a color red and a color blue. Okay, so I take a product of 2 5 vertex model, but I could do it with K colors. Okay, but now these models are going to interact. And the way they interact, so I gave an example here, is we get an interaction, okay, whenever a path exits to the right and it's color blue, and we have a red path too. So why did we define those interactions? This comes from the theory of symmetric functions again, is that these correspond to what are called co-inversion LLT polynomials. Okay, so they are indexed now not by one partition, but by a k-tuple of partitions. And so when you do that, what does it give you when you look at, for example, losange tilings? Okay, so I'm giving you an example for 2 tilings. So for example, I could take 2 hexagons, okay, with A, B, C shape. So of the same shape, here I chose, but I could choose some of different shape. I'm tiling each hexagon with 3 types of losanges. And now I'm going to superimpose my 2 tilings. Okay, and I want to compute this generating polynomial. I'm going to sum on all these K tilings, but not only just their product, I want to count them according to their interactions. Okay, and you're going to have to believe me that the interactions are exactly when the blue tile is of this type, okay, and the red tile is pointing up or the same as the blue tile. Okay, so let me give you an example. So I couldn't superimpose them and we could see something. So they are next to each other. Okay, so I have the same two hexagons. I tile them with lozenges. Okay, and I want to count the number of interactions between these two tilings. Okay, so I claim that this and this, because they are the same tiling at the same position, they're going to give me a type 2 interaction. And for example, this tile and this tile, they are going to give me a type 1 interactions. Okay, and my counting problem is to count these two tilings according to the number of interactions. Okay, and if you look, for example, here, I have 5 interactions between my two tilings. And so here is an example when you take k equals to 2 and with small numbers of a, b, and c. And so you get these nice polynomials, okay, in T. So what do we know about that? So as I said before, okay, all is built up so that it corresponds to LLT polynomials. So we know that this generating polynomial is a specialization of this symmetric polynomial in LLT that's indexed by k tuples of partitions. Okay, but what's pretty funny, well, I don't know if funny, is that the number of tilings with no interactions and k colors are in bijections with tilings of just one hexagon, but with a different shape. Okay. And the same way, the main term is also in bijection with tilings of just one hexagon, okay, but again of a different shape. And finally, there's some easy kind of symmetry. So that should be a T inverse there. P of ABC is some factors times T of CBA. And so what can we do with this is that finally, if you look at big two tilings of the hexagon, so here I fix B to equal to 2A, C is equal to 3A, and we make A becomes really big. And for example, when T is 0, okay, because of this nice combinatorics that's behind, relating the K tilings to the one tiling of a different shape, we can compute the arctic curves of these two tilings. Okay, what's kind of weird is that actually the two tilings have exactly the same curves, even though the interactions are not symmetric. So that's something we don't understand. And basically, we don't understand too much, except for T equals 0, 1, or infinity. So T equals 1 is just no interaction, so it's just a normal case. Okay, and on Monday, David will tell you how you can do these things now with K domino tilings. So I'm going to stop here, and I thank you for your attention.
Thank you for this very inspiring talk. So the questions or comments? Yep.
I have maybe technical questions. So could you come back? So where you were proving this evaluation of Q hook with Q hooks? So was the boundary condition changing? Because I thought that it's hard to change boundary condition with the Young-Baxter relation. So can you say how that was?
No, but the boundary condition doesn't change. Because the shape gives you the. So the bottom is the empty partition, the top is the empty partition, and the shape lambda gives you how you mix white and gray.
Oh, so these things on the right, that is not boundary condition? You kind of had these particles on the right, that's not your boundary condition?
So, but they move, they stay with the gray, you know, like.
Okay, maybe I will ask you.
Okay.
It's related somehow. I mean, how important is it to start with the empty partition? I mean, suppose that you start with any partition.
So actually, you can start and end with any partition. The only difference is then this is not easy to compute. So you can rewrite it as some kind of, again, a problem that is hard to compute. So.
This one has this specific boundary condition.
Like here, you cheat because this one is just frozen.
Yeah, of course, yeah.
But the same idea could work for anything on the top and bottom.
How important is the fact that you can have as many rows or as many columns as you wish in your partitions, meaning that number of particles to the left or a number of holes to the right is essentially infinite? And what happens if you have a restriction on their number?
Yes, so if you try to make a partition that would fit in a box, for example, you can't use the Yang-Baxter equation. It doesn't hold anymore. At least it doesn't give you a nice commutation. So it's very important that the rows are infinite.
Sorry, can you repeat just how this factor 1 over 1 minus q to the h appears? Because I didn't understand that, because you just you have in the previous slide.
I cheated. I didn't tell you how I put weights on my vertex model. But
yes, but I think the previous slide is some Yang-Baxter equality, right? And there should be a 1 divided by 1 minus q to the something in that equality, or not? The previous slide?
So here?
The previous. Maybe more actually.
Yeah,
There.
So
yeah.
These have weights, and the weights are going to give you exactly those. Maybe I can explain to you in detail. I kind of hid the
Okay. Yes.
So each row is going to be indexed by some kind of power of q, you know, and it's going to work exactly that what's going to pop up each time is going to be the hooks. So.
Other question?
So do I understand correctly that all the weights you're using here are kind of dictated by the fact you have to have this Yang-Baxter equation? So for instance, your interaction T in the end, it's there because there's a solution of the Yang-Baxter equation for colored models, which has this T, right?
Yes.
So are you using all the possible parameters that Yang-Baxter solution are giving you, or just some?
No, so for example, there's way more complicated colored vertex model
Yes.
in the papers of Agarwal, Borodin, and Wheeler.
Right.
As we stayed at the level of LLT, because basically at first what we were looking is like proofs of the Cauchy identities.
Yes, but in
coming
principle,
from
you
this
have
LLT.
more complicated weighting also for your tilings, for instance.
Yes, you could
okay.
generalize to more complicated tilings models.
Okay.
But we're already stuck at the baby level.
Yeah.
But I don't know, maybe the way is to make it very general and make things easy. Like.
Other question? No. Okay, so we thank the speaker again. And so we meet at 2:30 then, since the second talk has been cancelled. Okay.